Hello everyone. Welcome to the second lecture today. My name is Shangzhe Chen. I'm one of the organizing committee members at MLSS 2021 Taipei, and I'm an assistant professor at National Taiwan University. Today, it's our great honor to have Professor Cho-Jui Hsieh with us. Professor Hsieh is an assistant professor in the computer science department at UCLA. So this is just a coincidence that both of the two lecturers today are from UCLA. Professor Hsieh's work focuses on improving the efficiency and robustness of machine learning systems, and he has contributed to several widely used machine learning packages, including the famous liblinear package. He's the recipient of the NSF Career Award, Samsung AI Researcher of the Year, and Google Research Scholar Award. His work has been recognized by several best paper awards in top conferences like ICLR, KDD, ICDM, and many more. And he will be talking about neural architecture search and AutoML today. So Professor Hsieh, please, the time is yours.
Yeah, thank you very much for inviting me here. So I'm very happy to share some of the recent advances in neural architecture search. So today, originally I was planning to talk about both NAS and also other AutoML algorithms, but I found actually if I only talk about NAS, it's already around 3 hours. So I'm going to focus on the neural architecture search part. Okay, so before I start, I want to thank my student Rochen Wang who helped me to prepare the some of the slides in today's talk. Yeah. Okay. So so neural architecture search has become a very important area in recent machine learning community. So everyone know. Sorry, let me open my slide. Okay. Yeah. So so neural network have been widely used, and in different, even for like image classification, there are a lot of different neural network being designed by human beings. Like people keep improving the design of convolution neural network, and even recently, people start to find like a transformer-based model can outperform convolution neural networks. So the human design networks are keep improving, and the main question we want to study in neural architecture search is whether we can automatically design the architecture of neural network. And this is not only for like a classification task, but many times when you face a new, like a particular task in some particular domain, you may want to automatically find the best neural network architecture for that problem. So you can design some problem-dependent neural network to improve the performance. And there are many successful stories in recent years. For example, the right figure I'm showing here is called the efficient net architecture. So this is like a combination of a human design and neural architecture search. We try to search. So this is developed by Google. They try to search for the backbone of these neural networks, and then they try to design using some human knowledge to design the scaling rule to scale this up. So today I'm going to talk about the recent progress in neural architecture search. So how do we automatically design the architectures? Okay, so outline, I will first talk about some background, including some history and some benchmarks people are using for doing research in neural architecture search. And the second part, I will focus on the significant progresses in the past 3 years. And there are, from my point of view, there are two most significant progress, including the differentiable neural architecture search and the predictor-based neural architecture search based on graph neural network. So I will focus on these two category of algorithms in today's talk, and then I will discuss some open problems and the future work people are trying to pursue. Okay, so so in today's lecture, I'm want to give you like the most recent algorithms in NAS. So in the future, you can probably use it in your own problems, or even if you want to conduct research on NAS. I hope this will give you a very good background for doing that. Okay, so the history of neural architecture search. So in early there are already some papers trying to study how do we automatically design the architecture of neural network, like even before 2000. Like this paper we found in 1989, people already try to solve this problem. But most of them are only able to scale to toy example, or they are only playing with very small scale problems. So none of them can be useful in practice. So earlier work usually used two types of algorithms. The first one is the evolutionary algorithm. So you can think finding the neural architecture is like you can have a pool of the architecture. You test the performance for each architecture in your pool, and then you try to evolve your population pool based on, like in evolution algorithm, they try to improve the population pool based on recombination or mutation. And in Bayesian optimization, they try to learn some performance model and using resampling to improve the current pool. So those algorithms are very time consuming because every time you have a population, you need to evaluate each architecture in your pool. And evaluating an architecture is equivalent to training the architecture from scratch and then compute the validation performance of the final network. So if you want to evaluate 100 architectures, then you need to do 100 times of the training, which is very time consuming. Okay, so just for fun, this is one of the earliest paper on neural architecture search in 1989. So you can see they try to solve some toy problem, like this is the XOR prediction problem. You have a two-dimensional problem, you want to fit the XOR data. And then you have some human design network, and the rightmost one is the network found by the evolutionary algorithm. But you can see this is very small, like only few neurons. And that time people can only scale to these small problems. So the main breakthrough for neural architecture search is at 2016. So there are two teams, one from Google, one from MIT. They both proposed the reinforcement learning for neural architecture search. So in these two papers, there are two main contributions. The first one is they propose a better representation for the search space. I will go over in the next slide. And they try to define the architecture search. Instead of trying to find the edge or the operations, they try to define NAS as the control problem, and they try to learn the controller to generate architectures. So the breakthrough in 2016, you can see they show, so ResNet and DenseNet are very widely used human design architecture for image classification. They achieve very good test error on CIFAR10 data. And you can see the RL-based NAS in 2016, they can achieve similar performance with human design architecture. However, there's also a problem here. So you can see the search cost. So this is the Google paper. The search cost is like more than 20,000. So GPU days. So it's impossible for any other research lab to reproduce this result. Okay, so let's try to briefly review what is the reinforcement learning for NAS. So this is not today's focus. I will focusing on more accessible algorithms developed recent years. So I will just briefly mention this reinforcement learning algorithm. So in the Google paper, they show instead of finding the whole like a graph to formulate the architecture, they try to define architecture search as a control problem. So for every layer, they try to have a controller. So this is the recurrent neural network controller. So every stage, they get the previous state, and then they output the next configuration. For example, here I try to say the filter, the height of the CNN filter equal to 3. And then next position, I try to output the filter width. And the prediction, if the RM predicts 7, then you put a 7 here. And then you try to predict 1. So they encode the architecture of a neural network into a string of configurations. And then they use a recurrent neural network to generate this string of the configurations. So this makes the search much easier, because instead of trying to evaluate a lot of different networks, you want to train your controller using reinforcement learning. So the algorithm is like this. You have a RNN controller. Every time you use your RNN controller to generate a series of configuration like this, this will corresponding to your current architecture. So you generate the architecture A with probability P, and then you train the network to see what's the performance of this current architecture. And then you have a feedback loop to the controller to update the parameter for the controller using reinforcement learning. Okay, so this is, although this is probably faster than like a pure evolutionary algorithm, but this is still extremely slow. So as I mentioned, you need more than 20,000 GPU days. So after this work, there are several improvements to reduce the search cost. Some of them are still used in current research. So for example, this is called the NASNet. They are trying to design a better search space. So instead of, previous work before 2016, they usually try to direct search on the whole neural network. For example, you want to search for a 100-layer neural network, then your search space is like all the 100 neural networks satisfy your configurations. So that will be very large search space. But in the cell-based, in this cell-based search space, people try to redefine the search space using the intuition from ResNet. So in residual network, this is most widely used human design network. Yeah, so there's a question, why is RL better than brute force search? So because RL is actually, this is a very good question. So I didn't mention, but because the RL is actually trying to constrain your search space. So originally in brute force search, you want to find any any set of configuration, but in RL-based agent, because your configuration can only generate by the recurrent neural network agent. So it's actually a constrained generation. So you cannot reach all the search space, but it's easier. So you reduce the search space by, the search space now becomes equivalent to the like a parameter size of the controller. Yeah. Okay. So now all the people are working on this cell-based search space. So in the cell-based search space, we are using the intuition of the ResNet. We are trying to design the network like this. So you have the input image, and then you have some normal cell repeated by n times. You have some reduction cell to adjust the size of the channels, and then you have another normal cell repeated by several times, and then a reduction cell. So you try to assume all the normal cells follow the same architecture, and all the reduction cells follow the same architectures. So instead of directly searching for 100 layers, now we only need to search the configuration for the normal cell and the reduction cell. So the space becomes much smaller than the previous search space. So you can see in this case, the reduction cell, if you look into the reduction cell, they try to specify you have several nodes in the reduction cell, and each node can connect to the other node, and then you try to search for the operations connecting each node. Okay, so this becomes the most widely used search space, which we still use in current research. Okay, so this gives, in addition to reduce the searching time, this also gives some flexibility. For example, you can use less blocks in searching because you only care about the architecture of normal cell and the reduction cell. So, for example, you can use 12 or even fewer, like 8 blocks when you do the searching, and then you try to stack this to 20 cells in the inference time. Or you can also generalize between different architecture, different data sets. For example, if you have, for example, you have a network for CIFAR-10, because you just already have the architecture for normal cell and reduction cell, so you can easily generalize this to the ImageNet by stacking different numbers of reduction cell and normal cells. Okay, so this makes the search very easy. So compare with the reinforcement learning paper, this can both reduce the test error and also the search cost, because you're getting a much more structured search space. This is kind of regularization to make it easier to find the better structure. Okay. So people also apply evolutionary algorithm to this like a NASNet search space. So in evolution, I will not go into detail, but basically in evolution algorithm, you have you work on the same space, you still do the population base, and then you generate some config, you evaluate, and then you refine your population. So all the works before 2018 are following either reinforcement learning or evolutionary algorithm. So you can see people starting from 20,000 GPU days, people keep decrease it to hundreds of days. However, even if it decreases to hundreds of GPU days, it's still very impractical for typical users, because not only so this is only the search cost for one search, and you may need to do the search for several times, depends on different hyperparameters. So the search cost is actually more than that, and this is not affordable by the users. Okay, so the expressing with NAS are typically time consuming. So before 2018, most of the works are from like big companies. So you have search algorithm and you need the performance evaluation several times. So every performance evaluation is like training the architecture for example, 100 epochs. And then you need to run this for different hyperparameters. And then you need to run multiple runs to report the mean, because if you just run one time, this may be you're getting lucky, you find a good architecture. So usually in this community, we need to run multiple times to report the average, and this becomes very expensive. Okay. So today I'm going to talk about how do we reduce this thousands or hundreds to less than one. And those are the important progress in the past 3 years. But before that, let me talk about some evaluation problems in neural architecture search and some benchmarks people are using. So evaluation of the neural architecture search algorithms is hard. So you can see many papers try to say they are outperforming others, but in practice, this may not be the case. And because there are many different settings when they report numbers. For example, you have the best versus average performance. For example, you can run the NAS for 10 times, 10 random seeds, and then report the best one. Then you probably can get a very good architecture because you repeat this 10 times and pick the best. But if you report the average time, the numbers may not be that good. So we usually want people to report the average performance with standard deviation instead of the best performance, because you can get lucky for the best performance. And also there are many different training recipes, which can significantly influence the performance. So you can see in this figure from the paper, ICOR paper, like this paper has very interesting title, NAS evaluation is frustratingly hard. So they are trying to say, even for the same NAS algorithm, if you use different training recipe for the final architecture, you can get very different performance, varying from 95% to almost 98%. And you can see the NAS performance, usually the difference is less than 1 or 2%. So sometimes when you see this number, this may not be due to the better algorithm, but it can be due to a different training strategy. Like maybe they use better augmentation, or they use training for more epochs. So the community really want to standardize this final training stage to make the algorithms comparable. And also there are many different search space. Like before 2018, I already introduced several different search space. So everybody try to develop their own search space and then report the numbers. So it's very hard to know which one is better. So after that, we recently we already have very good benchmarks for new architecture search. So one benchmark people widely use is this NASNet we just introduced here. So we try to standardize this and becomes, so most of the recent algorithms try to experience on this space. And in addition to this, because the NAS space is, you typically, like I mentioned, conducting experiments on NAS are expensive. So many people are trying to help the community in the sense that they try to evaluate the architectures in the search space, and they try to release the performance of those architectures. So for example, this Google paper in 2019, they try to release like for more than 400,000 architectures in the search space, and then release to the community. So later on, if you want to do the search, if you want to query an architecture that is already within this database, then you can directly use the results. You can directly get the performance instead of training the architecture from scratch. So this can save a lot of time when you try to develop a new algorithm. And one problem here in NAS Bench 101 is that they only contain architectures with less or equal to 9 edges. So because the space is very big, so they can only report the architecture with under certain constraints. So this may not be suitable for some particular algorithms. Like most of the today, I'm going to mainly introduce the one-shot method, which cannot use this NAS Bench 101. Later on, we will see why. And then after that, there are also several other NAS Bench, including one-shot one. So this is like an extension of 101, but they try to exhausted all the architecture within a smaller search space, so making it easy to run the experiments. And also Bench 201, in addition to CIFAR 10, they also build a benchmark for CIFAR 100 and like smaller ImageNet models. So later on, I will report when I talk about different algorithms, I will mainly talk about the performance comparison on NASNet, but sometimes I also talk about the performance on these benchmarks. So there's a question, very long. Let me read the question a little bit. Once the policy. . Yeah. So once you have a reinforcement learning agent, then you can produce any architecture. So the cost is how to train that reinforcement learning agent. That will cost you like more than 10,000 GPU days. But after getting the agent, it will be easy to apply to different problems. Is the benchmark hardware dependent? So very good question. I think this benchmark is hardware independent because in these three benchmarks, we only care about the test accuracy or test error. And I think in this clear, there are some hardware dependent benchmark. People just release like within 1 year. Yeah. So the difference between the NAS and neural network pruning. So in neural architecture search, there can be different goals. One goal could be to reduce the model size. In that case, it could be compared with the neural network pruning. So the performance. So if they try to search for the smaller model, then it's a different algorithm, but you can compare with neural network pruning. They probably perform differently based on different problems. But the main goal in neural architecture search is not only to reduce the model size. So our main goal is so you have some objective and you want to find the architecture to maximize or minimize that objective. So for example, in all the algorithms I'm talking to get, we are focusing, our objective is not the network size. Our objective will be the test error, test accuracy. So we want to find the best architecture to improve the accuracy, and pruning cannot improve the accuracy. What is the input in NAS models? So NAS is the algorithms. You define the search space, you run the algorithm, you can find the architecture. So this will give you the architecture. I think you don't need to. The only input is the search space, but the search space usually is encoded in the algorithm. Yeah. Oh, you also need to give the algorithm what's your objective. Like I mentioned, your objective can be test accuracy, or can be the model size, or there are also something called multi-objective NAS. So you want to balance the model size and the test accuracy. So you also need to specify your objective in the algorithm. Okay. So this is the background part. And next I will talk about the main progress after 2018, and I will make this extremely clear because I want to make sure you fully understand these algorithms. So the first algorithm I will introduce is the differentiable NAS algorithm. The other one is the predictor-based NAS algorithm. And the predictor-based NAS algorithm was actually already used before, but it becomes very useful recently due to the advance of graph neural network, which we will see later in the lecture. Okay, so differentiable neural architecture search. You can see in this table we are listing the progress after 2018. You can see those are a lot of algorithms. The search methods are not RL, not evolution. They call differentiable NAS, and they can achieve similar or even better performance than the previous work within one search GPU days. So let's see how can we do this. Is the NAS benchmark having the constraint of number of parameters? So yes, they So last benchmark. So the one-shot one and 201, they both define a search space, and then they compute the performance of all the architecture within the search space. So within that search space, you cannot have too many operations because the number of operations is constrained by the search space. Yeah. Okay. So the most important idea proposed in 2018 is called the weight sharing. So previously, assume you have several nodes and you have the connection. So the first neural architecture, you have the connection from node 1 to node 2, and then node 2 to node 3. The second architecture you are having from 1 to 2, 2 to 4. So in the original algorithm, both evolution and reinforcement learning, you have to train these two architecture differently to get their performance. So to get the performance of path A and path B, you have to train two different separate neural networks. And the idea of weight sharing is saying, because in these two architectures, they are sharing the path from 1 to 2. So can I assume, for example, if the 1 to 2 is a convolution operation, can I assume this convolution operation from node 1 to node 2 share the same weight, convolution weight? In the convolution, the weight is the kernels you're getting. So if I assume those two paths share the same weight in from node 1 to node 2, then if I get the weight for every operation on every edge, then I don't need to retrain another architecture. When I get a new architecture, I can just try to get the weight for this edge and another weight for this edge, and then I can directly get the performance for this architecture. So the idea of weight sharing can significantly reduce the computational cost for performance evaluation, because you can avoid retraining each new architecture. So I'll make it more concrete here. In 2018, there's a paper called ENAS. So they try to say we define the supernet to be the ensemble of many architectures. So this is actually something like this supernet. If you can see my cursor, it's the right bottom panel here. So for example, this is the case where you have 4 nodes and you have the edges between the nodes. For each edge, you have 3 operations you can choose. So for example, from 0 to 1, you can choose convolution or pooling or skip connection. From 0 to 2, you can also choose from these 3 operations. So in each architecture, you only have 1 operation activated in each edge. But in the supernet, you assume all the operations are activated. And then you train the whole network with all the operations activated to get the weight for every operation on every edge. So this is called a supernet training. And then once you train this supernet, you get all the W associated with each colored edge. So for any architecture you want to evaluate, you can just, for example, you have the if you choose the red edge in the from 0 to 1, then you can just use this W, this weight for your final architecture. You don't need to retrain your architecture. So for any configuration, you can directly get the weight from the supernet instead of training them from scratch. So they propose they still use a reinforcement learning algorithm, but they replace the performance evaluation stage by this supernet evaluation. So they assume they assume weight sharing, and they train the supernet in the beginning, and then when they do the reinforcement learning, every time when they need to query the performance, they just get the weight from the supernet and then evaluate on the validation set. So, so what does the node represent? Yeah, so good question. Let's try to define. So each node represents some. So in the search space, we are trying to have some node, and in this example, I'm assuming the edges are, you want to search for the operations on the edges. For example, let me go back to the to this. Okay. So for example, this is the NASNet search space. Each node is like this. So for example, the first node is the input from the previous layer. So the input feature from the previous layer. And then for each node, you connect to several nodes. In the connection, you specify which operation you want to do. For example, this node, they are doing convolution 7x7 and then pass the result to the second node. And then this node, they do the convolution 5x5 and passing the result to the second node. And then this node add them together and then pass them to the next node. So the node represent the features, and the edge represent what operation you want to do to you conduct the operation on this feature and pass this into the next node. Okay. So another example, I will have some more example later on. So you can see these are some search results. So you have the so in this case you have some two input features. The input feature go through the 3x3 convolution, go to this node, and this one go to skip connection, go to the second node, and then add them together, and then you go to the next node. Okay, so this is the definition of the search space. Okay, so can we use the same weight for different features if we share the weights? For different, I'm not sure what do you mean by different features, but if different feature means for the same node you have different input features, then yes, we are using the same weights no matter what input feature you're getting. Yeah. Okay, so ENAS is trying to do this in two stages. So they train the supernet and then do the RL algorithm, and they can reduce this to 0.5 GPU days and get very good performance on C++10. But what we further want to do is, can we do this in a single stage? So can we directly obtain the final architecture through supernet training? So we don't want to do the supernet training and then use another algorithm to find the architecture. We try to see if there is an approach to directly find the final architecture during supernet training. So this is possible, and this algorithm is called the differentiable neural architecture search. Okay, so let's state the problem clearly. So as I mentioned, there are nodes. Nodes represent the features. Like a 0 usually means you have the input feature from previous layer, and then you pass this feature through some operation to the next node. So our goal is to select which operation you want to use on each edge. So for example, you can have convolution 3x3, convolution 5x5, 7x7, skip connect, several options. So there are also options like 0, which means you don't pass this, which means you zero out the operation pass to 1. There are also some operation called none, which means you don't use this edge. So you can also do a topology, search for the topology if you have the none operation. Okay, so So we eventually want to find one operation per edge. So this is the discrete finding problem. So that's why people are using evolution algorithm or reinforcement learning. But the idea of the differentiable architecture search is we try to do a continuous relaxation to the problem. So wait a minute. Okay, so we assume, so here for simplicity, I assume there are two nodes and there are three operations, O1, O2, O3. There can be any operations. I just give an example here. So the input feature map is called V0, the output is called V1. So we can say V1 is the output of this equal to, if I give a weight to each operation, then V1 equal to alpha 1 times the first operation plus alpha 2 times the second operation plus alpha 3 times the third operation. So O1 of V0 is the, for example, this is, if this is convolution, then this is a convolution of the input feature. If this is skip connection, then this is passing the passing the input feature to the next node through skip connection. Okay, so we add a weight associated with each operation, and we assume the output is the weighted average of these operations. Okay, and then because the weight, we want this to be like a probability, from the probability sense, we want alpha 1, alpha 2, alpha 3 to be between 0 and 1, and then sum equal to 1. So we want them to form the probability distribution. So usually, instead of directly using this, we can assume this is the softmax. Alpha is actually a softmax probability. So this will automatically normalize into the probability simplex. Okay, but for simplicity, I will sometimes just use the first expression because it's easier to understand. But in practice, many times we're using the softmax here. Okay. So in the original search problem, you want to find one hot vector for each edge. So one hot vector means 1, 0, 0, 0, 1, 0, or 0, 0, 1. You only allow one edge to be non-zero, and all the others should be 0. This is the notion of choosing one operation for each edge. And in the continuous relaxation, it's very simple. We don't know how to solve this discrete problem, so let's try to relax this to a continuous problem. So we relax alpha 1, alpha 2, alpha 3 to be continuous numbers between 0 and 1, and they form the simplex. So for example, if you use this softmax assumption, then you don't need to assume they are in a simplex because this will be a probability. So there can be any continuous numbers. And then you relax the so once you relax alpha 1, alpha 2, alpha 3 to be continuous variables, you can formulate neural architecture search as a continuous bi-level optimization problem. So I try to, our goal is try to find the alpha, the best alpha, corresponding to the probability of each edge, such that the W star, which is the neural network, once we get the alpha, we can train the neural network to get the W star. And then we try to find the alpha to minimize the validation error of the final network. Okay. So let me state this again. So given alpha is the architecture parameter. So alpha determine how much weight you are giving to each operation. So it's corresponding to the architecture you want to choose. So given the alpha, you try to obtain the best weight by conducting a training, minimizing the training error. And then your goal is to find the alpha to minimize the validation error the best alpha to minimize the validation error, assume your W star is obtained by training the network using alpha. Okay, so this is called a bi-level optimization because you have a first level which you find the alpha to minimize the validation loss, but in the inner level your W star is related depending on alpha. Your W star is the argmin of W based on the training error. Okay, so if we can solve this problem, then we can get the. So if we can solve this problem under the constraint such that alpha is 1/2, then we can solve the neural architecture search problem. But in practice, we cannot enforce the 1/2 vector property because this will make the problem discrete. So we drop the 1/2 constraint and we make alpha continuous. So this becomes a continuous bi-level optimization and can be solved by gradient-based optimizers. Okay, so how to solve this optimization if we assume alpha is continuous? So in theory, this is still hard. So in theory, if you want to solve this problem exactly, at least in a concave setting, then you need to solve the inner problem exactly, which is impossible in neural network. But heuristically, we can still apply stochastic gradient descent to solve this problem. So when we apply like a stochastic gradient descent, we just try to iteratively update W and alpha. So you have two parameters. W is the weight parameter, alpha is the architecture parameter. You just alternatively update W and alpha. When you update W, you try to. So this is like a typical training stage. You compute the. Oh, sorry, I forget to add the gradient here. So this should be the gradient of the training error, and then you use the gradient of training error to update W. And then when you update alpha, because alpha is the top level corresponding to the validation error. So you fix W and use the gradient of the validation error to update your alpha. Okay. So this is very simple algorithm. You alternatively update W and update alpha. Okay. So there are also ways to solve this better. So in order to make it better, we can consider the second order optimization. So this is called the second order dots. And the main idea is here actually we have an approximation. So we assume when we update alpha, we assume W is fixed. But actually W is something depending on the latest alpha. So when you update alpha, your W will also change. So if you want to incorporate this into the optimization, into the gradient computation, so your gradient of the validation error, the first parameter is W prompt, but now we assume this is not a constant. This is something depending on alpha. And the second parameter is still W. Okay. Also, so the second parameter should be alpha. So this should be alpha. And then if you want to if you assume W prompt is the optimal solution given alpha, then it's very time consuming. You need to assume the optimality condition, which is probably not true. So a commonly used technique in people use a lot in meta learning is that they try to approximate W star by one step of the gradient descent. So instead of consider W prompt to be a fixed parameter, they consider W prompt to be W minus eta times gradient of L train. So plug in this one into here. And then if you compute a gradient of alpha and gradient of W, you can get the first term is the same with the previous updates, but the second term will be the Hessian. This will be the gradient with respect to both alpha and W multiplied with some gradient, some vector. Okay, so we do the, so how do we compute this Hessian vector product? So there are two ways. You can use finite difference. So if you perturb W by some small epsilon times the vector, the direction of V, then you can get the finite different estimation of this Hessian vector product. If you think this is inaccurate, then you can just compute by auto differentiation, which is only constant time slower than the gradient computation. Okay, so in practice, in the Dart's paper, they propose both second order and the first order algorithm. But after that, most of the people are using the first order algorithm because you can see later on, you can see there are many other problems for Dart's. Optimization is only a small problem there. There are many other problems, even if you can solve the optimization better. Okay, so there are some questions. Are we fixing the depth of the architectures and only searching through the type of operations? So yes, we are fixing the depth of the architecture and only search for the type of operations. And the depth, so this is the search space. The depth can be controlled by repeating this cell for multiple times. Then you can increase the depth. Like I mentioned, usually when you try to improve the performance, you need to use more depth in the final evaluation step. So will the alpha be similar for different operations? So this is something we're going to talk next. So it's in the original Dart, it's possible that alpha is like a 0.3, 0.3, 0.3. So it's harder for you to choose a final one. But there are ways try to promote the sparsity of the alpha, yeah, which we will introduce later. Okay, so in the Dart's algorithm, once you use either first order algorithm or second order algorithm to find W and alpha, then you can just use the alpha to choose the final architecture. So, do I have the? What is? Yeah. So once you use the so this is the Dart process. We can see in the beginning you initialize by uniform distribution. You run the bilevel optimization. Eventually you get something like this. So for some edge you have very strong signal whether you want to choose this one. For some edge you don't have a strong signal. But either way, in the final stage, you try to you try to use the magnitude of alpha. You try to choose the operation with the largest alpha for each edge as the final operation. So W is the model parameter. Yes, W is the model parameters and alpha is the weight of the operations. So you can see, yeah. Yeah, so alpha value corresponds to the weight we put in each operation. And W is, for example, in CNN, if it's a convolution, then W is the convolution kernel, the parameters for convolution kernel. Yeah. Okay. So the time complexity, the complexity of the differentiable neural architecture search. So this is called the Dart's algorithm. The time complexity, you can imagine you're updating W and updating alpha alternatively to solve the supernet. So it's equivalent to training the supernet only once, and the supernet has k operations per edge. Assume k is some constant like 7 or 10, then the algorithm will be less than k times slower than the standard training. So theoretically, it's k times slower than standard training, but sometimes because the GPU computation can benefit more, so the speed up will vary a little bit from k, but theoretically, it's k times slower than the standard training. And this is usually good enough because k is a small number, like 7 or 10, and like I mentioned before, if you want to do the RL or evolution algorithm, you need to evaluate thousands or 10,000s of architectures, and here you only need to do 7 times the standard training. So this is much faster, and this is why we can make it less than 1 GPU days. And there's in terms of memory, in terms of memory complexity, there is actually a problem. So when you do the backpropagation on SuperNet, so when in the optimization, we need to compute the gradient. We need to compute the gradient for W and alpha. So for both of them, we need to do backpropagation on the whole SuperNet, which means, but your SuperNet is k times larger than the original one because you have k operations on each edge. So the memory complexity for dots is k times memory consumption than the standard training, which is so this sounds like okay, like 7 or 10 times, but it can, because this is the constraint with the GPU memory. So for example, if you have 11 gigabytes GPU memory and your model size is like 2 gigabytes, then if you have 7 operations, then you're going to be out of memory and you cannot run this algorithm. So this makes the search prohibit for many problems. And later on, we will talk about how to remove the memory bottleneck. Yeah, so good question. How do we how do we obtain a discrete weight after the training? So here we are. This is the DARTS algorithm. After training, you get the continuous weight, and then for each edge, you try to choose the operation with the largest weight. So for example, the first edge 0.84 is the largest, so you choose the red one. From 1 to 2, the green one is the largest, so you choose the green. So how many steps in the by optimization are usually taken? So usually between 10 and 100, but that's also a little bit tricky. So I will talk about it later. So later on, people find training more iteration will actually hurt the performance, and we'll talk about that. So what is the intuition? Why the SuperNet training working at all? So this is like the intuition is like in this bi-level optimization. So if you have the bi-level optimization and you have alpha being discrete constraint, then this is equivalent to the original NAS problem because your alpha, you want to choose the best discrete architecture to minimize the validation error. So this is the original problem. And the only relaxation we make is to relax alpha from discrete to continuous. So this is like intuitively, this is like a common practice in many machine learning algorithms. If you want a discrete solution and it's hard to solve, then you can relax it to a continuous one. And then finally, you project it back to the discrete domain. Yeah. Okay, so the performance so DARTS also work on this NASNet search space. And so as I mentioned, there is this memory consumption issue. You need k times more memory, GPU memory. So you have to search on fewer cells in the search space. And then they try to search, they need to reduce the size in the searching stage. So in the searching stage, they try to use fewer cells, and fewer channels. So for example, in the DARTS paper, they use 8 cells and 16 channels in the search space. 8 cells means they stack this cell by 8 times. Yeah. And channels means in the convolution, they use a smaller number of channels. And then when they train the final model, they stack this the same block 20 times and increase the number of channels for training the final architecture. And later we are going to solve this. There are work trying to solve this problem, so we can reduce the memory consumption. If we can reduce the memory consumption, then we can directly search on the final size we want to use. Also, very good question. Do we directly use the search weight after NAS, or do we retrain the model on the search architecture? So we retrain the model on the search architecture, because given architecture, we want to find the best W for it. And because due to the weight sharing effect, the W we are using in the search space may not be the best for the architecture. So we need to retrain it to get the final W. Okay, so this is the performance. You can see it's comparable to other previous method, but you can significantly reduce the search cost to 1 or 4 days. But actually, this is using the GPU in 2018. For now, I think if you run DARTS, it's less than 1 day. Okay, so yeah, another question about why it works. So later on, I will also talk about this. So you're worried about the weight sharing assumption, right? And actually, many people are worried about it. So that will become the main problem in DARTS, and it's an unsolved problem. Yeah. But we will briefly talk about some analysis about the weight sharing, and they are actually showing weight sharing may not work very well. Yeah. Okay, so as I mentioned, we can also transfer to ImageNet. So we so DARTS they can use the architecture and transfer to ImageNet. You can get decent performance comparing with other architecture search methods. Okay, so those are the architectures found by DARTS. Just some examples. You can see there are several convolutions and skip connections, and some poolings, skip connections. Okay, so we're going to talk about the cases where DARTS fail. So in this table, it's very promising, right? You get very good performance, you get very small cost. But later on, people found DARTS actually doesn't work even on very simple search space. So in this paper in iClear 2020, they defined 4 very simple search space. The first space only have 2 operations per edge. They selected from the original DARTS SuperNet to make sure the best performing architecture are still within this search space. The second space have 2 operations, conf and skip. The third space have 3 operations, and the fourth space have 2 operations. So all of them are very simple space. For example, in the third space, in the second step, you only have conf and skip. In the space 4, you only have conf and Gaussian noise. Gaussian noise means you just you have an input feature, but you just replace it by Gaussian noise and add to the next node. So it's it's a non-meaningful like operation. So you can see they try to study darts performance within this very simple search space, and they found the problem, as many people expect. There are problems for darts. So you can see the validation error of SuperNet is actually going down. So those 4 curves corresponding to 4 search space. So different color corresponding to different search space. So we can see for all the space, when you solve the bi-level optimization problem, the validation error is going down. But when you try to check the test error of the final architecture, as your search epoch increase, your architecture becomes worse and worse. And there's a sweet point here. And for some of the space, actually, it blow up very quickly. So they are showing darts actually doesn't work in those 4 spaces. And also, previously, some people ask how many iterations we want to train for SuperNet. So this showing actually increasing the iteration is harmful. So you don't want to train for many iterations. Okay. So so there are some questions. Gradient-based NAS is faster load, but in practice, would it still be non-gradient-based NAS for better performance? So yes, so that's why I have 2 topics today. The first one will be the gradient one, and the second one we try to still use the standard performance evaluation, but using some trick to make it faster. Yeah. So in practice, it's you need to depends on problem. There could be different pros and cons. Yeah. Okay, so yeah. Yeah, so we will talk about the so I think I can answer this question after talking about that. So I'm going to discuss what I think is a good case when you so I think briefly saying, I think that is really very dependent on the search space. And if you have a good search space, then I think Dart is fine. But if you have very wild search space, then I don't know how I'm not sure how it will perform. Yeah. But let's try to see this interesting finding. So let's look into the why darts fail. So we can see the test error going up. So what's the architecture found by darts in those 4 space? We can see in space, in the first space, this is the final architecture. All the edges are skip connection. So you can see, so if you're familiar with the ResNet, then skip connection means you don't have any parameter you want to learn. So if you don't have, if for all the edge you are having skip connection, then this is like a degenerated neural network, and you don't have any parameter you are able to train for this neural network. So this will perform very poorly in practice. And you can see for for the second and the third space, you can see almost all the edges are skip connection. Also in third space, all of them are skip connection. And in the fourth space, it's between the noise and the convolution. You can see there are many noise connecting to, for example, node 3 becomes non-useful, and there are many noise and there are only few convolutions. So you can see there's a very serious problem in darts. You get all the edge to be skip connection. So what's happening here? So there are 2 reasons. The first reason is the sharpness of the solution. So as we as I mentioned before, we are relaxing a discrete problem to a continuous problem, and then eventually we project back to a discrete solution. So a good continuous solution doesn't imply a good discrete solution. And I think this is what several people already asked in the chat. So people find, so what's the condition when a good continuous solution imply a good discrete solution? So we can try to formally characterize the gap between the continuous and the discrete solution. Assume my alpha star here is the continuous solution, my alpha bar is the discrete solution. Then by Taylor expansion, I can show my validation loss approximately equal to the validation loss of the continuous solution plus the alpha bar minus alpha star times the Hessian times alpha bar minus alpha star. So I can see the change of the validation loss when I try to project alpha star to alpha bar will be roughly Hessian times the distance from alpha bar to alpha star. Okay, so H is the Hessian with respect to the alpha. So so this corresponds to, in this picture, we can see what's happening here. So if you converge to a region like this, the left-hand side, if you converge to a very wide and flat region, then if you perturb alpha, so if you have a flat region, this means the Hessian, the eigenvalue of Hessian, the norm of the Hessian is very small. In this case, if you perturb alpha from continuous to discrete solution, then the performance will not change too much. But on the right-hand side, if you converge to a sharp minimum, if you project from alpha star to alpha discrete, then your performance loss will be huge. So people find in darts, usually you converge to some kind of this kind of sharp minimum, and this is the reason why the final projection step doesn't work. So in the same paper, they are also showing this first two figures we already seen before. So this is the validation. The SuperNet performance is improving. The final architecture is blowing up. And we can see, meanwhile, if you check the dominant eigenvalue of the Hessian, then it's also blowing up. So this means the darts is converging to a sharper minimum like this. So that's why the final discrete architecture becomes worse and worse. So this is the first intuition why the dart doesn't work. And the second one is interesting finding. So it's also interesting. So you can see, we see in the final architecture, most of the edge are skip connection, which is very surprising. Why skip connection will dominate? So we can, empirically, you can observe when the SuperNet performance increase, the weight for the skip connection will increase, but the weight for convolution will decrease. So as you train the SuperNet for more epoch, your skip connection weight will keep increasing, and eventually you get, after projection, all the edge becomes skip connection. So we can, so in our 2021 paper, we actually able to prove that if you train for infinite number of iterations and you got the optimal SuperNet, then as the number of layers grow to infinity, your alpha skip, the weight of the skip connection will converge to 1, and the weight of the convolution operation will converge to 0. And this is happened in the Dart search space when theoretically when your number of layers go to infinity. Okay, so this shows this is not only because the SuperNet optimization is not only because you cannot get a good SuperNet, it's because even if you get the optimal solution for the SuperNet, you're going to choose all the skip conventions instead of convolution. So we need to this is why Dart fails, and we need to. Many people start to study how to fix these two issues. So there are assumptions, including the search space is the cell-based search space, like a darts, what we use in darts, and also the layers go to infinity. Yeah. And also assume you can get the optimal supernet, which is also tricky because in non-convex optimization, you cannot get the optimal supernet in practice. Okay, so we're going to talk about how people are trying to fix those problems, including improving the performance and improving the scalability. Okay, so the first category is try to improve the supernet training for darts. So as we mentioned, one problem of darts is like they are doing continual relaxation, and we are not sure how So we're not sure how the continual relaxation performs, and actually many of you are skeptical to the continual relaxation. So another view of the darts is to rethink darts as the distribution learning problem. So I assume for each edge, I have alpha 1 to alpha k, similar to the original darts, but they are no longer the weight for each operation. Now I view this alpha as the probability of sampling each operation. And then we try to sample an architecture based on this probability distribution on each edge. And then, so you can see in this diagram, you have a distribution defined by alpha 1 to alpha k for each edge. And you sample an architecture based on this distribution. And then based on the results, you do the gradient computation, and then you have a feedback loop to the original distribution to update the alpha 1 to alpha k. So this makes sense because if you can, your goal is now not the continual relaxation anymore. What your assumption is now you have a distribution, you generate the architecture from this distribution, and you try to find the best distribution to generate the final architecture. And the question is, how do you define this distribution, and how do you use gradient from the continual or distributed sample? How do you get the gradient computation to update how do you backprop the gradient back to the original distribution parameter? Okay, so the benefit of this distribution learning view is that you can, because you're considering sampling from the distribution, so it tends to preserve better, the performance tend to preserve better after discretization. And there are also ways to enforce the sample to be discrete. In that case, you are enforcing the sampled discrete architecture to be good, and that will be an ideal training objective. And second, you can reduce the training time in some cases, as we will see later. So I think you're asking about the previous hearing. So intuitively, when you have infinite number of layers, so in each cell, you don't need to gain a lot more information. So the scale combination can be dominant because in each cell, after several layers, you already get a very good feature vector. So you can use the scale. Most of them can be scale combination when you have infinite number of layers. But if you're interested, you can go into this paper to see the formal proof. Yeah. Okay. So the first, so in the distribution learning paradigm, we have two things we need to think about. First, how do we define the distribution, and how do you backprop the gradient back to the distribution parameters? Okay. So this is not new in architecture search, because there are already several problems in variational inference. They already try to have some people already try to study how do you backprop the gradient through some sampling procedure. So gumball softmax is one important technique for doing this, and this is widely used not only in architecture search but also in many other machine learning areas. So in gumball softmax, the goal is to sample from a discrete distribution. So assume I is following the distribution parameters by alpha I. So if you just use alpha and then sample I, then you don't know how to update your alpha based on the performance of I. So in gumball softmax, there are two components. First, you use the gumball max. So mathematically, you can show this I is equivalent to argmax of I prime of Gi prime plus log alpha I. So Gi prime follow the gumball distribution, and log alpha I is the log of the original distribution parameter. So in this case, why do we want to do this? Because in this case, we can separate the sampling part and the parameter part. So later on, if you want to backplot to alpha, we don't need to consider G here, the sampling procedure here. And this is not enough, but this is not, the gumball max itself is not enough, because I is still some discrete variable, and you don't know how to prop to alpha. So we need to further relax this to softmax. We need to further relax the argmax to a softmax. So this is called a gumball softmax. You can see you relax this argmax to the softmax with some temperature gamma. So usually when gamma go to 0, this will converge to the argmax. So in practice, you can keep decreasing the alpha until it's very close to 0. And this will enable backpropagation to alpha 1 to alpha k, because now you can see you define zi to be this variable. So you can easily compute the gradient of zi with respect to alpha I. And if you have something performance defined on zi, then you can backprop back to alpha I. So this enables backpropagation through the sampling procedure. It's called the reparameterization trick. And also, so this is used in SNAS. The main idea of the paper is to use the gamma softmax with a neo temperature in dots. So they assume gamma is decreasing from a large number to close to 0. So eventually, this will be very similar to discrete samples. And as I mentioned before, you can make sure the architecture is not too bad after the discretization. Okay, so another paper called the GDAS, they're also using the gumball softmax trick, but they further. So here in the previous slides, ZI you can control the temperature to make ZI close to discrete, but it's still a continuous variable. But in the GDAS, they assume your ZI is you use the argmax, and then they use something called the straight through trick to backprop through the argmax. So the main trick is they assume Z bar I, which is a discrete version of Z. So they first sample ZI from the ZI is similar to here. This is the softmax version, and then they project it to the discrete version, and then they can write ZI bar as ZI plus constant, and then when they backpropagation, they just treat the constant as no gradient. and then they backprop the gradient from zi bar to zi. But the benefit of sampling zi bar, which is discrete, is that so now for each edge, you only activate one operation at each time for the backpropagation. So you can reduce the cost. You can reduce the training cost from k times to very small, almost one time, almost similar to the original CIFAR training time, the standard training time. Yeah. Okay. So you can see S-NAS, G-DAS. So if you use a continuous but annealing temperature to close to 0, you get slightly better results, but also similar cost to the original DAS. But if you make it discrete, then you can also improve the search efficiency. Okay, so the next algorithm is the Dr. NAS. So instead of using Gumbel Max, we try to use the Dirichlet distribution as the distribution sampling of the sample distribution of alpha. So you can see we assume alpha is sampled from some Dirichlet distribution parameter by beta 1 to beta k. So so in this case, we're assuming alpha is not a softmax, but is sampled from the simplex, which is so usually that distribution is like a sampling from the k-1 dimensional simplex. You can see if you have three operations, then you're sampling from the probability simplex. If your parameters, so the parameter magnitude controls whether your sampling will closer to a particular operation, and the size of magnitude of the beta controls whether you have sparse or the dense samples. So for example, here you can see if the beta are very small, like 0.85 for each beta 1, beta 2, beta 3, then your sample will concentrate on the corner part of this simplex. So very close to discrete and with high variance. But if your beta is very large, then your sample will concentrate on the central part of this, which is all the operations have similar probability. So in this case, you can control the sampling procedure from continuous to discrete, and also you can directly make it in a simplex. Okay, so I think I will skip the gradient computation, but the objective function for Dirichlet neural architecture search is that we can formulate this as a distribution learning problem. You assume your alpha is a distribution defined by beta. So instead of finding the optimal alpha, you try to find the optimal beta such that the sampled alpha will maximize the performance. And you have some regularization to constrain your beta to be close to some prior distribution. So we can show this if you use the Dirichlet distribution and have a regression term, then you can implicitly in the search procedure, you're controlling the sharpness of your hashing matrix. So we can show this is your training objective. The validation error of the sampled alpha can be upper bound of the validation error plus some trace norm of the hashing matrix. So it's equivalent to you are minimizing your validation error, but you also regularize your hashing to avoid the blowing up dominant eigenvalue. So you can see if you use darts, then when you increase the search epoch, your hashing eigenvalue will increase. But if you use the dirichlet neural architecture search, then your eigenvalue will decrease. So you can see this can further. This is currently the best performing distribution-based learning algorithm for DARTs, and you also have small cost similar to the original DARTs algorithm. Okay, so finally, so before so maybe I will finish this before the break. Yeah, so as I mentioned, we sometimes also measure the performance on the benchmark data sets. So this is the NAS Bench 201. So you can see the Dr. NAS algorithm can achieve very high performance, and on one of the data, actually it can find the best performing architecture in the whole search space. So because in benchmark you can know what's the best architecture, they already compute the performance for every architecture. So on CIFAR 100 we can find the optimal architecture, so there's no room for improvement here. And for all the other two data sets, it's also very close to the optimal architecture. Okay, so so let me finish this part. So there are several other algorithms for trying to make DARTs tolerable to discrete projection. So another algorithm is called the NASP. So if you're familiar with like a linear regression and lasso, then you'll see usually when people try to get a sparse solution, they try to add some constraint or regularization to the problem. So here we try to add a constraint to the bilevel optimization problem, such that your alpha is constrained in a simplex. Such that your alpha can only have one single element to be activated and all the other element to be 0. So we have to make sure your alpha satisfies these two constraints. So your alpha will still be discrete. So this is like in DART's problem, we don't try to do the continual relaxation. We keep the discrete constraint, but we try to directly optimize the original discrete constraint. So this is you theoretically you cannot solve this discrete problem in polynomial time, but in practice you can apply some projective gradient descent algorithm for doing that. So the projective gradient descent is very simple. The idea is every time you update your alpha by the gradient, and then you project your alpha to this constraint set. So in this case, it's equivalent to you do the gradient step on the alpha, and then you find the best architecture for each edge, and then you only use that as the next alpha. So so in this algorithm, this is called the NASP. And you can see the search cost is very low because every time you project to a single operation, so the cost is maybe just the same as the standard training. But the test error is a little bit higher. And the main reason is that it's easier. You can imagine it's easy to stack in local minimum because your alpha is always discrete. You update your alpha by a small gradient step, and many times it's not enough to move your alpha out of the original architecture. So it's easier to stack in some discrete architecture and cannot explore other architectures. Okay. So this is a final algorithm for making it easier to discretize. So the algorithm, intuitively, you want to make your loss landscape smoother. So this is the original, the left-hand side is the original DARTs landscape. You want to make it smoother like this too. So how do we do that? One very simple idea is you want your supernet to be robust to the perturbation of alpha. So if in the original one, if you perturb your alpha a little bit, then the accuracy will change, the loss will change a lot. But if your network is robust to alpha perturbation, then even if you discretize this, it will not sacrifice too much of the test accuracy. So so to make the supernet robust to alpha perturbation, we propose two algorithms. The first one is to make it robust to random perturbation, and the second one is make it robust to adversarial perturbation. So I will not go into detail here, but if you want to make it robust to random perturbation, then the only thing you need to change in the original DART algorithm is when you have an alpha, you add the Gaussian noise to this, then you will be also, sorry, I think it's not Gaussian. So here I'm saying this is uniform distribution, so actually add a uniform distribution. But in general, you can use any distribution. So you just add a random noise to your alpha, and then you do the same thing as original DART. In the adversarial version, you just update your alpha by the gradient of the alpha. So this is like a one gradient ascent stage to find the worst case perturbation of alpha, and then you do the same DART update. So this is extremely simple and turns out it's pretty useful. So in these figures, we try to monitor. So as I mentioned before, in many other algorithms, if you train for many more epoch, the supernet test error will blow up. Like here you can see in the left figure, we train for more epoch, the supernet performance will blow up. But if you use this regularization, like adding random or adding adversarial perturbation, then your supernet accuracy, your performance will going down as you train the supernet more. And you can also see the dominant eigenvalue of the hashing is going down using this regularization. And the benefit of this approach is you can add to many other, because you can see the only thing you need to add is changing. This is like one line in PyTorch. The random one is like one line in PyTorch. The gradient one is like few lines in PyTorch. So you can combine this with any other differentiable neural architecture search methods. And we can consistently improve their performance. Okay. So those are the the tricks people are trying to improve the supernet training of darts. And you can see in the end, the supernet performance can be improved as you train the supernet better. Okay. So there's one question. Can you say again about how we get the optimal in the benchmark? So in the benchmark, because it's like there are some search space and they already compute all the performance of all the architecture in the search space. So this is like a database. You can query the minimal error. Then this is like an oracle in that benchmark. Yeah. Okay. So let's maybe take a 10 minutes break here. So I'll stay here for answering question, but I'll start to talk about the second part in 10 minutes. This is what time in? So I guess everybody may be in different time zone, but in 10 minutes, yeah. Oh, okay. Yeah, so there was a question about the what? How do they compute all the architecture in the search space? So they basically enumerate all the architectures. For each architecture, they try to train it from scratch, like for maybe 100 epochs, and then get the performance. Yeah. Yeah, if there are other questions, feel free to ask. Oh, okay. So differentiable NAS doesn't have a. How quickly does this NAS controller learns? How many gradient updates? So usually between 10 and 50, but it depends on yeah, 10 to 50 epochs. Because you only need a rough idea of which alpha is larger, so don't need to train for too many epochs. Yeah. Can we do NAS on low spec computer? So if you want to do so I think there are there may be two scenarios here. The first one is you want to do the search using a low spec computer, then in that case I think like if you have one GPU, then you can still run darts on like a small search space. So I think darts is the only one. I mean differentiable NAS. The methods we're talking in the first part will be the only feasible ones. Yeah, but if you are talking about the low spec computer for the inference time, then there are many NAS algorithms they try to search. So as I mentioned in the beginning, you in the search you are going to define some objective, and you want to search the architecture that optimize the objective. So if your objective is if your objective is like the final architecture should be efficient on low spec computer, then this a very commonly used case. Yeah. Yeah, like for example, searching on for architecture on mobile device, or there are also people searching on different chips. Yeah. So in many use cases, I think people are trying to search for the better architecture for a certain hardware device. That's one important application, and that's already useful in practice. Another, if you want to get the best performance, many algorithms are using NAS. For example, as I mentioned in the beginning, so before the transformer, the best architecture was the efficient net, and the backbone of the efficient net was searched by the NAS algorithm. Yeah, but as I mentioned, they are trying to combine human knowledge there. So once they find the backbone, they try to use some predefined rule to scale it up. Oh, so that's a different, that's a totally different work. In ImageNet in minutes is that's work just focus on training. Yeah. So for hardware constraint, there are two. You can formulate it in the objective function. So for example, you can formulate the latency as some function of the architecture, and then you can constrain the latency to be. You can try to minimize the latency. Yeah. And if you have multi-objective, like you want to balance the inference, you want to balance the inference speed with the performance, the accuracy, then you can have two objectives, and then you have some parameter to balance these two objectives, and then you can, based on different parameter, you get a different balance between the two. Usually, yes. If it's not, then you can. If it's not, then it's also trickier. Then you cannot use that. Yeah. Okay. Okay, so let's continue the second part. So we talk about the in the first part we talk about darts and how to improve the SuperNet training. And now we are going to talk about how do we improve the scalability, and also how do we do the architecture selection. Okay, so I will make it quicker because we have the second part about non-differentiable architecture search. So for the scalability, as I mentioned, the two problems. One is the training time, k times slower than the standard training, which is not, it's k times slower, but it's usually okay. The main difficulty is you have k times memory cost. K is number of operations. So in many DARTS pipeline, they try to search on a smaller number of cells and then generalize to a larger number of cells in the inference time. And the question is, how can we reduce the memory cost to directly search on the full network instead of the smaller network? So we call this smaller one the proxy task. So can we direct search on the end task instead of using a proxy task? Okay, so one approach is using it's called a proxyless NAS. This is also one of the first paper discussing this issue, and the idea is very simple. So similar to Gumbo softmax one, they are using a sampling-based approach. So when you use the sampling-based approach, every time you sample architecture, you sample the operation on each edge, and then you backprop through this edge. So in this case, you can try to avoid backprop through all the other operation. So there's a little bit trickier than what I said, because if you just do the gumball softmax, then remember there's a z variable which is still depends on all the architectures. But in this paper they try to assume you only sample one path. You try to adjust the probability for this path, and then you just normalize all the other paths to make it probability simplex. So if the selected path is good, then your weight will going up, then all the other operation will going down. If this path is bad, then this will going down and all the others will going up. So, but the idea is very similar to the sampling based NAS. Okay. So in addition to, so in this case, you can reduce your operation level memory usage, because every edge you only use one operation. And another reduction you can make is to reduce the channels. So in convolution neural network, there are a lot of channels. Like in many operations, there are channels. So in this method called PC-DARS, they try to randomly drop the channels in the search time. So this is like a dropout, but they drop out the channels, and they found it will not affect the performance too much. And because you drop a lot of channels, you can save a lot of memory. And in one of our 2020 paper, we try to say, instead of doing the dropout randomly, you can progressively prune the channels. So initially, you can use a large dropout rate. And then once you identify some channels are having very small weight or they are not important, then you can directly remove the channel and then reduce your dropout rates for the rest of the channels. So you can progressively reduce the dropout rate from a large number to 0, but keep the similar memory consumption if you do the progressive pruning. But so this is the results. We can see the search cost will be So we are taking Dr. Nuts as an example. If you use the original method, then you can only search on the proxy test, then it's 2.54. If you search on the final end architecture, then it will reduce to 2.46. Okay, so the final part about the DARS algorithm. So we talk about SuperNet selection, and we haven't talked about how we make the projection. So most of the papers previously are talking about how you improve the SuperNet, but actually in one of our papers, we found the projection step is actually important. So in the original projection step, usually you have an edge with a large alpha, then you're going to choose this edge. But we are arguing this is the wrong approach. And this is, in theory, this can give you very bad results. And you have to use another way to do this. Okay, so the motivation is from the previously we talked about the cases where DARS fail, and we show there's skip domination problem. So for the optimal SuperNet, we show the skip convention will go into 1 and the convolution weight will go into 0. So this means we are going to always select the skip convention if we train the SuperNet well. So this is a counterintuitive, right? Is intuitively we don't want our network to have all the edges skip convention. We want to have some convolution. But in theory, if you train the SuperNet perfectly, then your skip convention will go into 1. So all the edge will be skip convention. So the main problem here, we think, is maybe the alpha value of each operation doesn't mean the operation is more important. So the assumption that we should choose the operation with larger alpha value may be invalid. And this is the main idea in this work. So we're asking, does alpha represent the operation strength? So probably not. For example, if you use the alpha magnitude, you're going to choose most of them to be ski convention. But if you use other way, you can choose some convolution, many convolution operations. And to validate this hypothesis, we try to conduct the experiment. So here, we try to compare the alpha value. So each of this figure is the configuration of one single edge. So in each edge, there are 1, 2, 3, 4, 5, 6, 7 operations. The alpha is the magnitude of each operation. And the orange bar is the performance of neural network if you select this operation and keep all the other supernets remain the same. So it's like the whole supernet remains the same, but you project this edge to a certain operation. What will be the performance? So you can see if the alpha magnitude corresponds to how important is this operation, then the blue bar should be correlated with the orange bars. But in many cases, they are actually in the reverse order. So you can see there are no clear correlation between the two. This means the magnitude of alpha is not really correlated with how important is this operation in the supernet. So we propose a new architecture selection method. In the architecture selection method, it's actually similar to pruning. So every iteration, you try to look at one single edge, and then you try to drop each operation on this edge to see what's the performance loss. And then you choose the operation with the smallest performance loss as the final operation. So every time, so this is like a leave one out evaluation, right? So every edge you try to leave one out operation, see how the performance loss, and then choose the most important operation. And then after that, we found you have to fine tune the solution for few epoch to before moving to the next edge. So this is called a perturbation-based selection. And we can see so we mentioned a lot of improvement over DATS in the recent years, but with this perturbation-based, if we change the final selection, architecture selection method to this perturbation-based selection, then even the original DATS algorithm can be competitive with the recent proposed ones. So you can see there are on the original space where DATS fail, like in the original CIFAR 10 S4 space, DATS can get very bad performance, like a 7.2 test error. But if you use the PT or the proposed projected based perturbation-based selection, then this can reduce to 2.64. So this is very close to the best method recently proposed. So this is consistently improve overall original DATS on multiple space. And furthermore, you can see the performance in the original DATS. If you increase the training epoch of the search, your performance will drop. So this is corresponding to the previous figure we see. If you increase the search epoch, then your testing error is going to blow up. So this is the accuracy is going down. But if you use the perturbation-based selection, the accuracy will remain similar. And so you can see if you use DARTS plus PT, this is already 2.6, competitive to many recently proposed methods. And this can also combine with all the other methods, because all the other methods are trying to focus on the supernet training, and PT is for final projection. So for any supernet you combine with this, you can get better performance. So finally, we're talking in the DARTS, we're going back to the original DARTS formulation. So in DARTS formulation, you have the operation parameter alpha, and you have the weight parameter. So we are asking the question whether, because in the perturbation-based architecture selection, we don't really use the magnitude of alpha. So we're asking the question, can we just remove alpha in the original DARTS? And the answer is this will work to some extent in many cases. So you can see in many cases here, if you use a fixed alpha means alpha is fixed to be a uniform distribution and you don't do the alpha updates. This can be very competitive with the original DARTS plus PT. But this is only on different search space, there will be different phenomena. There are some cases where with the alpha version will be still better than the one with fixed alpha. So where people are still trying to figure out whether what role alpha is playing in DARTS, and whether we can reduce alpha in the original differentiable neural architecture search. So very good question. So why don't we just use a supernet as a final architecture? So usually the supernet doesn't give you very good performance because it tends to overfit the validation data you are using. So usually the projection step will improve the test performance. Okay, so I will conclude the differentiable NAS part by some problems people are trying to solve. So first problem, as many of you already being skeptical, so whether the weight sharing assumption is valid. And actually it's for certain spaces it's not valid. So this is like I think this is some natural language processing space, and you can see if you try to do the weight sharing, then so the bottom bars, those blue bars are the actual performance of each architecture. So there are 30 architecture they evaluate here. Let's sort by the actual performance here. And if you plot the performance with weight sharing, you can see there's no strong correlation between the weight sharing performance and the actual performance. So this is showing weight sharing is failing in this search space. So as I mentioned, in practice, we found DARTS is very sensitive to the search space. But probably some search space you can do weight sharing, some search space you can't. Oh, so the fixed alpha means in the original DARTS we have alpha. So let me go back to the in original DARTS you initial alpha by uniform, and then you're going to alternatively update alpha and W. So fixed alpha means we fix alpha to be uniform. So we don't update alpha. We only update W in the supernet. So it's equivalent to just training a supernet without updating the architecture weights. Okay. Okay, so because the weight sharing doesn't work for all the space, so there are very recent work trying to say you can do few shaft NAS. So one shaft NAS means all the architecture share the same weight. So you only train one shaft supernet. Few shaft NAS means you split the space into several parts, and each group of architectures are using the same, are doing the weight sharing, but between different groups, there are no weight sharing. For example, in this figure, you partition the architecture into 3 groups. So each group have their shared weights, but between group, they are using different weights. So, and they show better performance in several cases. So this opens the area where how do you identify when to share the weights? And this corresponds to how do you know when the task will work, when will not, when will it not work? And how do we incorporate how do you do the task with like a partial weight sharing? So all of those questions are open. Okay, so as we see, there are many problems. The assumption of the darts may be incorrect. The weight sharing may be incorrect. So another line of work still trying to keep improving the predictor-based NAS, which is not using the weight sharing assumption. And we're going to talk about recent advance in this area. So okay, so let's revisit the NAS problem. In the original NAS problem, we try to find the best architecture, the discrete architecture, to maximize the validation accuracy. And the problem we are facing is that the validation accuracy is very expensive to evaluate. So, for example, in genetic or in evolutionary algorithm, every time you want to evaluate your architecture, you need to retrain it from scratch. You need to train it from scratch. So it's very expensive to evaluate the validation accuracy for one architecture. So one of the solution, this actually has a long history, is to use a surrogate predictor. So instead of evaluate your architecture to get a performance, you can train the performance predictor. So here I use F tilde as the performance predictor to approximate the validation accuracy of any input alpha, any input architecture. So if you can get a very accurate performance predictor, then you can just use performance predictor to evaluate the architecture which have no cost. And then you can just choose the best architecture based on your performance predictor. Okay. So the very simple idea to implement this concept is you collect a lot of a small set of architectures, so maybe hundreds of architectures, and then you train each of them to get the performance. So for each architecture in your pool, you get the accuracy, and then you train the predictor to fit this. So this is a regression test, right? You want to have a predictor given the input new architecture, you want to output the final performance. And if you can train this very accurately, then you can use this to select the best architecture. Okay, so this is usually, this sounds good if you can get a very good predictor, but usually if you want to get a very good predictor, you need to collect a lot of data. So we have to do this iteratively. What do I mean by iteratively? So, we to use this in practice, we iteratively pick training data for the predictor. So this is like you can check this. You can see this diagram for the procedure. So you have a current pool of architectures, and then you do the training to you use the current pool to train the predictor. And then you use the predictor to identify some new architectures adding to the training pool. And then you evaluate those new architectures and then do the training again to refine your predictor. So you can do this again and again to iteratively refine your predictor. Can we make NAS more explainable and interpretable? I guess this is the open problem. I don't know. And it's hard to say what do we mean by more explainable and interpretable. Yeah. Okay. So how to train the predictor? How the training data set is collected? Can you please briefly explain again? So how to train a predictor? So you collect, for example, you collect 100 or 1,000 architectures. You train each of them fully to get the final validation accuracy. And then you have some neural network as a predictor. To the input is the architecture, output is the accuracy. So it's like a regression problem. And I haven't talked about the structure for the how do we define this predictor. So the predictor can be any machine learning model, but later on we will see the main the reason why this becomes very useful now is because we have a very good way to define the good predictor here. Okay. So yeah. So this is like a you can think this is like an active learning scenario. You have a initial pool of samples. You do a training to get your model. You use your model to get to query which what are the next set of architecture you want to evaluate, and then you add this to the training pool to refine your predictor. And this will usually be better than the static setting where you collect a set of predictor and train the collect a set of architecture and train the model. Yes, if you get a perfect predictor, then you can just find the architecture to maximizing the output. So you can just enumerate all the architectures and then pass each of them to a predictor and then find the best one. Yeah. If the predictor is perfect, but apparently it's not. Okay, so you can see, so this is the figure showing the iterative data selection improves the predictor for top model. Also this one. So you can see ignore the blue curve, but the solid red curve is the iterative the performance of iterative predictor based model, and the dashed curve is the if they don't use this active learning idea, they just collect the pool of the architectures and train the predictor in one time. So you can see there's a significant gap between those two. If there are different architectures in every iteration, should we retrain the surrogate model? Yeah, so you retrain or fine tune the surrogate model every iteration. This is like every time you have new architecture, you have to update your predictor. Yeah. Yeah. So this is showing the iterative algorithm will so interestingly it will improve the performance for top models, but it will actually sacrifice the average performance. So eventually the predictor will try to guide you to a region where the performance are better, and they try to make the correlation better for the top models, but they may not get the overall better correlation. But it's fine because we only care about the top models. Okay, so the pipeline for predictor-based NAS, as I mentioned before, you have the training pool of architectures. You label the pool by train the architecture and evaluate on the validation set. And then you use the pool to train the predictor, and then you use the predictor to propose new architectures. And then the architecture will pass to you will augment to your training pool, and then you're doing this again. So we need to talk about how do we define the predictor and how do we propose new architecture based on the current predictor. So first, we'll focus on how do we propose new architecture. So the architectures with high predicted accuracy. So there's a balance between. So if you have a predictor, one naive way is you just always propose new architecture that are you just propose new architecture that are top K in the predictor model, but it may not be a good case because this your current predictor may not be perfect, so you may need some exploration. So how to propose a new architecture is actually a balance between the exploitation and exploration. So you want to focus on more promising regions of the architecture, but you also want to have a better coverage of the search space. So it's like a exploration and exploitation problem in active learning or in online learning. So in practice, there are trade-offs between these two. So we need to use some, but luckily this is already studied in the literature. So many algorithms already proposed for solving this trade-off problem. So okay. So formally, in addition to, instead of using the predictor score to directly output, we define some acquisition function such that we are going to choose the top K based on the acquisition function, the score in the acquisition function, and this function may not be totally correlated with the predictor model because we want to balance the exploration and exploitation. So for example, there are two extreme cases. If we set the scoring function to be the predictor, f tilde is the predictor. If we set the scoring function to be the predictor performance, then this is corresponding to you always choose the top predicted model. So this is 100% exploitation, but no exploration. On the other hand, if you always choose random model, then it's 100% exploration, but no exploitation. So you want to balance these two. Okay, so by the way, once you get the scoring function, you are going to choose the top K based on this scoring function. So very good question. Can we transfer the other predictor to this data? I haven't seen much work on this, but I think it's possible. But so later on, I will talk about some pre-training technique, which is similar to this, but not exactly the same, because transfer learning is like you have other label data and you transfer to this one. So I think that's a interesting direction. Yeah. Okay. So there are several common choice of the predictors, including Gaussian process, NLP, so multi-layer perceptron, just fully connected neural network, and Siamese ranker. So different paper are using different predictors. So the key components of the predictor, they are trained differently, but they all composed with encoder part. So you have a neural network. Neural network is like an input architecture, and then you need to encode the architecture into some feature, and then you have the NLP or Gaussian process or the ranker to predict the score. But the architecture encoder is very important, and this is the main breakthrough in these few years. Because previously, for example, you can see the whole idea of this full framework is also used in hyperparameter search. So people are using this is very similar to Bayesian optimization in hyperparameter search, but in the main difference is in hyperparameter search, there's a natural distance between hyperparameters. For example, you can just use L2 distance or any natural distance. But in the new architecture search, the input is the graph, not like a list of continuous numbers. So you need to define a good encoder to encode those architecture into features. And this is and recently people find ways to, this can be done very nicely using graph neural network. And that's the main reason the predictor-based model becomes very popular recently. Okay. So another question, how much can a deep predictor actually learn in this setting? Yeah, so very good question. So we have very limited training data. How can we expect the predictor to be performing well? So one question, so one answer to this is I will introduce later. So they show you need to do the unsupervised pre-training stage for this encoder, which will significantly improve the performance. So because in unsupervised training, you are seeing a lot of infinite number of data, but they are unlabeled data, but that will help you to get a good predictor. And also, even though, so every time you only see hundreds of architectures, but another important factor is you don't need a predictor to rank all the architectures correctly. You only need a predictor to predict the top performing ones. So the predictor doesn't need to work on the whole space. It only need to focus on the top architecture. So it will make the learning easier. Okay. So next we'll talk about how do we define the encoder to encode the architecture into the feature vector. So there are many encoders, but the most successful ones are using the graph neural network. So we're going to talk about this. So naturally, you have an input architecture, and the architecture can be viewed as a graph. You have nodes, you have operations on the nodes or on the edge, and then you try to encode this graph into a latent feature. So this can be done using graph neural network. So graph neural is they are widely used in, for example, encoding the protein information or encoding some graph information. So like a protein is you can think input is in the protein functional prediction. You can think input is a protein, it's a graph between different nuclear, and the output is the function of the protein. So since GNN can do that pretty well, we expect GNN can also try to encode the new architecture pretty well. So I will not go into detail, but in graph neural network, usually you have the input feature for each node, and then you propagate you have a graph convolution operator here, which is equivalent to you propagate the feature according to the adjacency matrix, and then you have a linear transformation after that with a redo activation. So so finally, you get in GN, you get a representation for each node, and we use the sum of the node as the final feature. Yeah, so can we update SuperNet? I think this is about the previous part. So we can update the SuperNet and architecture parts at the same time. Yeah, so there are also work trying to do that in the same time. So they frame it as a single layer, but two blocks of variables. Then you can update alpha and W at the same time. So that doesn't matter too much, actually. Yeah. So the people show if you update them in the same time, you get similar performance. Yeah. Okay, so the pre-training, so as I mentioned, you don't have enough data. So if you do this training from scratch, you only have hundreds of data points to train your graph neural network. But the successful performance coming from the pre-training. So if you want to, so typically if you have a graph neural network, then you can do a standard supervised training, which is you have architecture mapping to the performance, and you don't have enough data for this. But you have almost unlimited unlabeled graphs. So any graph fitting in your architecture space can be an unlabeled graph. And you can sample almost unlimited unlabeled graph to pre-train your graph neural network. And graph pre-training, there are many different ways for conducting GNN pre-training. And one, for example, here, I give an example here is using, you can, so it's similar to the like a language pre-training. So you can mask some of the nodes or the edge or the node features, and then predict the node features or the edge. So to pre-train your GNN. So this is the like a unsupervised pre-training technique. And after unsupervised pre-training, you get a pretty decent initialization. So you don't need much data to get a good performance predictor. So this paper called ARC2VEC, they show the difference between pre-training with or without pre-training. So you can see the left panel here where the red point means you the lighter point, the red one means you have higher performing architecture, and the blue ones are lower performing architecture. So you can see if you do the pre-training, then the higher performing ones will be separated from the lower performing ones. If you don't have the pre-training, then it's like all of them are mixed. And you can also see this figure shows the correlation. So you can see if you do the pre-training, then it's more correlated. The test accuracy is more correlated with predictive accuracy. And otherwise, the correlation is less significant. Okay, so the color means the density. So yeah, this means many points are here. This means there are a few points here. Yeah. Okay, so finally we're going to talk about how to do the whole algorithm. So we talk about the predictor. We talk about the and we need to talk about how to use this predictor and integrate it with the proposal architecture proposal to get the full predictor-based algorithm. Okay. So we assume the predictor will give you will predict the so here we first assume for simplicity, we assume the predictor will give the Gaussian output. So we'll predict the mean to be mu of alpha. Alpha is the architecture, mu alpha is the predicted mean, and sigma square is the predicted standard deviation. And we can, if we assume this is a Gaussian distribution, then we can compute the expected improvement score if we include this architecture alpha into the new training pool. So assume F star here is the best accuracy in the current architecture pool. So we want to see how much expected gain can we increase this best current accuracy. So this can be mathematically computed by F tilde alpha. F tilde alpha is the architecture, the current prediction of the architecture, current performance prediction of the architecture minus the previous best architecture. And you have a hinge loss here, because if the new one is worse than the previous best one, then you don't have any performance gain. Okay, so you can compute the expectation of this this function. It will becomes, because under the Gaussian assumption, you can easily compute this. So it will become this term. So this term include the Gaussian CDF and the Gaussian PDF. And the most important thing is the gamma term here. So the gamma term here is, you can see the denominator of the gamma value is the standard deviation of the prediction, and the numerator is the mean minus the previous best. So the gamma value is the term balancing the exploration and exploitation. And because this can be computed mathematically, so you can just compute this for your architecture and then choose so use this as the scoring function, and then you have you can randomly sample a lot of architecture, compute this value, and then choose the top K score architectures. Okay. So in order to use, so this is like a okay, so this is like a standard Bayesian optimization algorithm. There's nothing new here. So the main difference is now, so for example, in typical Gaussian process, you assume the predictor will output a Gaussian distribution, the mean and variance of the Gaussian distribution. But here, our predictor is usually not a standard Gaussian process. This can be a GNN or some other neural network. So what people usually do is they have the predictor. So the predictor can give you the mean of the performance, and then you can try to estimate the uncertainty of the performance by some uncertainty quantification methods. For example, ensemble method is one kind of uncertainty quantification, and you can also use some Bayesian linear regression as another uncertainty quantification. So basically, you have some predictor, you can combine it with some uncertainty quantification to get the mean and variance, and then you assume this is a Gaussian distribution. Then you can use our formulation to compute the expected improvement, and then choose the top scoring architectures to add to the pool. Okay. So the training pool of the architecture, so like the training efficiency of the performance predicted NAS. So usually the reinforcement learning or evaluation need hundreds of GPU days. We already see differentiable NAS require less than 1 GPU days. And the predictor-based usually take around 10 GPU days. And the bottleneck is the architecture training, because for any newly added architecture in the pool, you have to train it for example, 10 or 50 or 100 epochs to get the performance. And it's time consuming. So in one of our recent paper, we proposed a way to improve the efficiency for this predictor-based NAS. So the idea is actually very simple. So in the training pool, there are many architectures. Some of them are very bad, some of them are very good. So for the very bad one, maybe after training few epoch, you already know it's very bad. So you can early stop those bad performing architectures. And for the better ones, you can train longer. And the training longer can help you to distinguish between the top ones and the best ones. So depends on the performance of the current training, you want to determine whether you want to train for more iterations or you want to stop at the current epoch. So if you do naive early stopping, which means you reduce the training length for all the architectures, then you tend to, for example, in the original performance, if you want to train 100 epoch to get the performance, you can assume the ranking doesn't change after one epoch. So you train all the architecture for only one epoch. And clearly this doesn't perform well because the performance after one epoch is very different from the performance after 100 epochs. So we need to do this called non-uniform successive halving. So for instead of training every architecture fully, we identify poor performing ones and stop them in the early stage. And then after adding some new architectures, we can choose whether we want to resume the previous stopped ones based on the intermediate results. So let me use this figure to explain the idea. So originally, it's not like a pyramid. It's like a full rectangle. So every architecture you have to train for many epochs. But now in the rank notch algorithm, it's like you have the bottom layer, all the architecture you only train for example, one epoch. And then based on the current performance, you decide a subset of them to upgrade to the second layer of the pyramid. So they will train by another maybe 2 epochs. And a part of them will upgrade to the next layer to be trained for 4 epochs, for example. So this can, many of the architecture will stop at the lower level and they don't need to be trained fully. And only the top performing ones will be trained fully on the top layer. And in the algorithm, as we mentioned, you are going to add some new proposals into this pyramid. So when you add the new ones, you can run this again. You can try to add these K proposals to the first layer, see how they compare with other post configurations in the first layer, and decide who a certain ratio to progress to the second layer. And the ratio should be the same as the initial setting in the pyramid. So in this way, you can guarantee the total performance can be reduced. And because if under the assumption that early stopped ones are not good, then the predictor can still nicely predict the top performing architectures. Okay, so this is the performance. So you can see using this non-uniform stopping, you can reduce the training time by more than 5 times with the similar performance. So if you remember, then the differentiable architectures usually the best one achieving like around 2.5% error, and this is getting similar and is faster than previous predictor-based methods. Okay, so this is the current status of the predictor-based methods, and so let's go to the conclusion. So today we mainly talk about the differentiable NAS and the predictor-based NAS. So as many of you are skeptical to differentiable NAS, there are several problems. So it's very efficient. So even if you only have one GPU, you can do experiments on NAS, but it's also less reliable. Although some issues were be able to solve by recent work, but there are still issues when you try to apply this to real-world problems, especially when the search space is EO-defined. Yeah, and the predictor-based NAS is a safer choice from my point of view. So you don't have weight sharing, so you don't have those skeptical assumptions. And although it depends on the performance of the predictor, but because your predictor will anyway keep getting new architectures, and for new architecture you have to train it to see the performance. So the performance tend to be keep improving, and it's more reliable, because in the worst case, imagine you sample. In the worst case, you sample most of the architectures, then you should have a good idea which one is the best one. So the weakness is, of course, it's slower than the one-shot differentiable NAS algorithms. Yeah, and also it depends on a good performance predictor. But I want to emphasize that the performance predictor, I think many people think the performance predictor is already very good. And I mentioned in the previous slides, there are NAS bench 101, one-shot 1, and 201. And actually this year, there's the same team proposed the NAS bench 301. And in 301, they try to say they want to cover a large search space. And how they cover large space is they just train a good performance predictor to they collect a lot of data to train a good performance predictor to predict the performance for any configuration in that large search space. And their experiments demonstrate the performance predictor, the error of the performance predictor is less than the error of using multiple training with different random seed. So in the neural network training, every time you start from a different random seed and you do a training, and they show the gap between the performance predictor and the actual performance is actually smaller than the standard deviation of the random initialization. So in most of the cases, so they think it's a reliable way to even evaluate the NAS methods. So the good predictor here, I just mean you can get very good performance. So you can predict the final accuracy. So you may not need to predict the final accuracy accurately, but you can predict the ranking accurately. Yeah. Yeah, but I think if you're talking about if we can, whether we can look into the GCN and see what are the important features for architecture to be good, then I think it's an interesting area. I haven't seen paper doing that, but I think it's reasonable because they claim they have a performance predictor which is similar to Oracle, so it should already learned something important. Yeah. Okay, so so finally, I will conclude with some interesting future recent trends and future directions. So one future trend, so one recent trend is remember in differentiable NAS we already reduced the time to similar to that's just constant to the standard training time. So the question is, can we further reduce it? And there's a recent direction called NAS without training. So you don't even train the supernet. You don't train anything, but you want to search for a new architecture. So the question is, can you choose a good architecture without doing any training? And they try to say, they try to claim there are some kind of zero-shot performance evaluator without training. So this zero-shot performance evaluator, they are just you can just compute the performance you can just compute those values based on the architecture itself and the input data, but you don't need to perform any training. So for example, before I go into the detail, let's see this figure. So the purple dashed line is some performance predictor with the increasing number of training epoch. And you can see increasing number of training data. So you can see there are some there. So each of these dots in the zero, the vertical line 0, they are the zero-shot predictor. So you can see some of them are very bad, like 0.5 is very bad. But so this is correlation between the true ranking and the ranking of this zero-shot predictor, ranking given by this zero-shot predictor. So if the ranking is 1, then this is perfectly ranking. This means the predictor can give the exact ranking of the true performance. So you can see the ensemble, there are several of them can get like around the 70, 0.7 correlation. If you do a voting, you can get 0.8 correlation, which is already similar to some like a performance evaluator, some trend performance evaluator. Okay, so let's see how they are doing this. The first work proposing this, they are trying to say if the neural network is good, then the neural network should have many different linear layers. So if so we are focusing on ReLU network. If the ReLU network, so the ReLU network is like a linear, it's like piecewise linear neural network. So for each region, it's a linear, but there are many different linear regions. So they try to estimate the number of linear regions. And in ReLU network, the number of linear regions can be estimated by the number of activation patterns when you pass the data into the neural network. So, so intuitively, if your network have more number of linear regions, then it's a better neural network. Okay, so of course this is also related to the weight of the neural network, but they just use the random initialization because this is not without training. So they just use the random initialization and then compute how many number of linear regions in this network. And there are actually multiple papers trying to do this. And another idea is using a neural tangent kernel. So I think you probably heard from the other talk about the neural tangent kernel. So this is a way to measure the trainability of a neural network. So because if you, under the linearization assumption, the neural network training is like a training on this NTK kernel. So under this assumption, the condition number of this NTK kernel can control how easy the neural network can be trained. And the idea is they can just use this, the spectral of this NTK, the condition number of this NTK kernel as the performance evaluator. So if it's very hard to train, then it's a bad network. If it's easy to train, then it's a good neural network. Okay, and you can see they show very high correlation with the performance. So the horizontal axis is the condition number of the NDK kernel for the given architecture, and the vertical axis is the test accuracy. You can see there are high correlation between the NTK condition number and the test accuracy. Okay, so using those approach, they can when you cut off. So there's a question: when you cut off the training of full architecture early, what value do you train the performance predictor on? So very good question. So I didn't mention the detail, but in the algorithm, because you stop some architecture early, so you only have the ranking between architectures instead of the performance evaluate, exact performance regressor. So instead of using the regression model, you have to train the pairwise ranking model based on if you incorporate this early stopping technique. Yeah, so because the ranking-based model, you only care about the ranking. So if it's early stop, then you expect it to be worse than the other architecture. So you still get the ranking information. Yeah. Okay, so in those NAS without training work, they show decent performance using zero-shot predictor. But I think it's still limited because you don't do any training, so you cannot expect it to get the best performing network. So the open question is, can we combine this zero-shot predictor with other methods like darts or like a predictor-based model to improve their performance? For example, in the rank notch algorithm, we're actually using the zero-shot predictor as the performance evaluation at the zero epoch. But I think there can be more like a genetic way to incorporate zero-shot predictor into the predictor-based NAS. Okay. Oh. Okay, so the next problem is about the search space. So there are already many algorithms proposed, but I think the research on the search space is still limited. So the current search space are too well defined. For example, we can see there are problems in the darts algorithm, but if you run it on some nicely defined space, then you cannot find the problem. So in order to better evaluate the algorithms, we have to have more diverse and different search space definition. And so in our group, we also try to apply NAS to real problems. And when we try to apply this to real problems, the most difficult problem is how do you define a search space when you face a new problem. Like we have a project try to work on FPGA, neural network FPGA, and we are not sure because the Dutch search space is very limited. So how do you define a good search space to be generic enough to include ideal architectures, but it's not too large to hurt your search algorithm. And also, I think the current search space is, if you naively define a search space, it can be either too simple. So any algorithm convert to similar solution, but they are not good solution, or maybe it's too difficult, so to take a lot of time. So I think difficulty in practice is how you define the search space. And also there are some people showing if you are working on a really well-defined search space, then a random search algorithm. So you just randomly pick architecture and evaluate it. It can also get very good performance. So yeah. So the search space definition is really important. Okay, so yeah, so how do we define a better search space to evaluate the NAS algorithms? And more importantly, in practice, because usually it's very hard to design a search space. So how do you automatically design a search space? Or is there a genetic way to find a search space for a problem? It's very important, I think. So there are several possible directions along this line. One is you start from some existing network and you try to upgrade this network. So every iteration you try to slightly change this network and to improve its performance. Another, and there are very few, but some work on that direction. Another one is how do you generate a neural network? How to directly use a generated model to generate an architecture from scratch. So you don't need any search space. You just need to generate a graph. So this is also interesting. And also related to this, in NAS, or I think in general in AutoML, there are general two directions. One is you want to go fully automatic, or you want to add more and more human knowledge into the algorithmal space to make it more useful in practice. So I think there's a balance between these two. And people are trying to pursue each direction. For example, you can see Google just published the AutoML 0 framework. So instead of, so in NAS, we try to search the operation on each edge, but in AutoML 0, they try to search in the operation level. So you have a computation graph and you try to search in the operation level. And this can, so you have, of course, you have large search space, but Google also have large TPU. So this can be a fully automatic framework for not only NAS, but also like automatic training or automatic tuning. Yeah. And however, currently the most successful real applications are usually you need to inject human knowledge into combine with NAS, like efficient net. So how to balance these two and which direction to go is also very interesting. Okay, so that's the end of this talk. Thank you very much, and I'm happy to answer any question. How do you evaluate the AutoML? So I think, I'm not sure if you mean using their provided AutoML algorithm, then I think you can do that. I heard they stopped maintaining that at a certain point, but I'm not sure. Yeah.
Okay, so we still have some time for some questions. So if you have questions, please type. And while we are waiting for more questions, I have a general question for you.
Yeah.
So nowadays a lot of machine learning research requires a huge amount of like computing resources. So it's hard for people outside of Google, Facebook, etc. So is it harder? Is the bar to conducting good research or entering the field of machine learning harder now? And do you have any suggestions to students or beginners in this field?
Yeah, I think you can focus on different kind of work. So I think if you want to compete, like for example, the ImageNet accuracy, you want to design some model to get the best ImageNet accuracy. It's probably very hard. But if you focus on other effects, like for example, in this neural architecture search work, actually most of our experiments are just using single GPU, like our GPU server, so a GPU machine, but it's not very fancy. So, so in academic, or if the student want to work on research, I think you can still find some problem with like important problems, but you don't need to scale to internet scale. You can just try to work on smaller data and try to demonstrate your algorithm works. Yeah.
Okay. Yeah. Thank you. Yeah. So we have more questions.
Oh, what is the instinct of NAS without training? Why can we use how many linear regions to models and so I think the question is about the why can it question how NAS without training. So I'm not a defender for the work, so I'm not sure, but I think for instance in the NTK work is kind of having some theoretical background, because if you train a neural network from scratch, from random, under like certain condition, you can think it's following the NTK kernel, and in that case, you are measuring the trainability of the neural network. But for this, how many linear regions, I'm not totally sure. I think their intuition is your network should have more different linear region, because if your network is degenerated into single linear region, then it's just a linear network and it's not very useful. But I also have a question why this can be measured, because you are using the random initial W, not the trained W. So I'm also skeptical to this.
Is it because it prefers like more complex models?
Yeah, it prefers more complex model, but but you are using random W, so that part I'm not sure. Yeah.
So if there's no other question, so actually I have another question.
Yeah.
So in the predictor-based method, we only use the architecture as input, and I was wondering what if we can compute some statistics of the data set. And so the input will be both the architecture and the input, and the label is there, the performance of this architecture on these data sets. That way we can train this predictor on different data sets and potentially get more data.
Yeah,
is it possible?
I think it's possible, but I haven't seen people doing this, at least in a large scale. So I think this.
I see. Because I remember many years ago there was a like before deep learning, there was a paper that uses some data statistics to predict which machine learning algorithm will work best on this, like SVM or random forest, etc. So I wonder if you can just put those data statistics, a feature into the predictor.
Yeah. I think that's interesting. I think one problem maybe less people working on that is because there are not many search space, and most people are working on C++ 10 data. So, but I think if we have multiple different, in practice, this could be very important. Yeah.
So there is a question about what is the relation between AutoML and explainable DNN mechanism.
Explainable DNN, I think they are different. So AutoML is like we try to make machine learning automatic, but we are not necessarily making it easier to understand. So yeah. but yeah. So explainable DNN, usually you try to, so I think there are several directions. There are several like sub problems in explainable DNN. So for example, how do you explain why the network predict this? And I think the other one may be more, so another one is how what are each layer actually doing. So that may be more related to architecture search, but people haven't tried to make it AutoML explainable, I think. Yeah, I haven't seen, so people try to visualize it and try to see when it fails, why it fails. Like I show you several figures. When you choose a lot of skip convention or some very or if all the edges are trivial, then there are some problem. But that's the only thing I've seen. Yeah.
Okay. So if there's no other questions, let's conclude this talk and thank the speaker again. Yeah, and actually, we will see Professor Hsieh pretty soon again, because he will also be serving as one of the panelists in the trustworthy machine learning panel discussion session on August 18th. So yeah, so if you are interested in how to make machine learning more robust and trustworthy, please join that discussion panel session. Yeah. So thank you again, Professor Hsieh.
Okay, thank you.
See you soon. Bye-bye.
Bye.